Εδώ, ναι, ναι. Όχι. Τι βλέπω πάλι.
Υπάρχει ένα μείον.
Ναι, οκ. Ναι, ναι.
Οπότε, Μάρια, αναλαμβάνεις, έτσι, μπαίνω στο background.
Ναι, ναι. Καλησπέρα κύριε Κρινή. Περιμένουμε λίγο για να μπουν και περισσότερα άτομα και ξεκινάμε σε λίγο λεπτά.
Δεν έχουμε πρόβλημα. Έχουμε ακόμα... Δεν είναι 7 η ώρα, 6 η ώρα ακόμα.
Αυτό, ναι.
Πώς πάει ο καιρός εκεί, κάνει κρυό?
Εδώ πέρα είμαστε στη χώρα του ήλιου. Δεν υπάρχει, δεν μας πιάνει τίποτα. Μάλλον δεν ξέρω.
Ακούω ότι θα πέσει θερμοκρασία 20 βαθμούς στις επόμενες μέρες ή ώρες.
Ναι, ναι, και εγώ έτσι ακούω, αλλά σήμερα έχει μια υπέροχη μέρα πάλι, δεν ξέρω. Πάντως, μέχρι τώρα...
Αρχίζει από το βορρά και κατεβαίνει σιγά σιγά προς τα κάτω.
Ναι, ναι. Βορειοδυτικά πιάνει και θα κατέβει, λένε. Είναι και ο Αντώνης είναι πρώην φοιτητής του μεταπτυχιακού και μετά πήγε και στο Αμπερντίν και δουλεύει τώρα εκεί για μια εταιρεία πρόσφατα. Συγχαρητήρια, Αντώνη, να σου το πω και από εδώ, για τη νέα σου δουλειά.
Μπράβο του, μπράβο του.
Ναι, βρήκε δουλειά στον τομέα και είχε μείον 23 από ό,τι ακούω.
Δεν συνηθίζονται αυτές τις θερμοκρασίες στο Αμπερντίν. Σε ποια εταιρεία δουλεύει?
Δεν θυμάμαι, πρέπει να μας πει.
Ah.
Clearwell, νομίζω δεν είμαι. Clearwell, ναι, καλά τη θυμάμαι.
Δεν πρέπει να είναι operators αυτοί, πρέπει να είναι service company.
Πρέπει, από ό,τι έχω καταλάβει, θα μας πει λογικά στο chat, μοιράσου, Αντώνη, άμα θέλεις. Πρέπει να είναι service για scale, για τέτοια treatments. Δεν έχω...
Οκ. Ωραία. Εσύ, Μάρια, τι είπαμε, κάνεις το μεταπτυχιακό,
Ναι, εγώ είμαι εδώ στο μεταπτυχιακό και τώρα κάνω τη διατριβή μου στην ουσία. Είμαι στο επίπεδο της εργασίας, δηλαδή.
Ναι, σε τι θέμα?
Είναι Machine Learning Applications in Reservoir Engineering ο τίτλος. Οπότε, ναι.
Όλοι σε αυτό, Machine Learning. Ωραία.
Νομίζω Machine Learning, Data, CCS, Geothermal, Energy Storage, αυτά τα θέματα πλέον είναι πάρα πολύ δεδομένα.
Κάθε 4 χρόνια, δεν ξέρω πόσο, έχουμε κάποιο θέμα το οποίο συζητιέται πολύ. Αυτή τη στιγμή είναι AI και Machine Learning.
Ναι, ακριβώς, ναι.
Προφανώς εμείς της παλιάς γενιάς δεν είμαστε και τόσο ενθουσιασμένοι με όλα αυτά, αλλά Ας αφήσουμε τους νέους να βγάλουν μια γνώμη για αυτά.
Και εμείς νομίζω απλά πρέπει να κάνουμε adapt στην κατάσταση. Δεν νομίζω ότι πολλοί απόφοιτοι από petroleum engineering έχουν γνώσεις coding τέτοιες έτσι ώστε να μπουν εύκολα στο κομμάτι του machine learning. Αλλά πρέπει να είμαστε εκεί που είναι η βιομηχανία τώρα, έτσι νομίζω.
Τι χρησιμοποιείς, Python?
Python, ναι. Κάποιοι χρησιμοποιούν και R, αλλά κατά κύριο λόγο νομίζω Python οι περισσότεροι. Η ώρα είναι 6, οπότε να το γυρίσουμε λίγο στα αγγλικά για να συνεχίσουμε. Οπότε, καλώς ήρθατε. Welcome everyone to our today's discussion titled Field Development Management, Opportunities and Challenges. Let's give it just a few more minutes because I believe more people will join us. In the meantime, my name is Marios Akritidis and I will be the moderator of today's discussion. I'm a master student in petroleum engineering at Technical University of Crete, as well as the president of our SP student chapter. I would like to thank Dr. Krinis for accepting our invitation and being here with us today, as well as Professor Varotis, of course, for bringing us in contact. Before we start, I have to mention that this meeting is already being recorded and it will later be uploaded to our YouTube channel. So you can watch it at your own pace and get the maximum benefit out of it. During the webinar, we invite you all to ask. We want a lot of questions. So all your questions should be addressed at the chat box and will be answered at the end of the presentation. As always, please keep the chat professional at all times. Today's session will probably last approximately 1 hour to 1 hour 30 minutes, depending from the load of questions we will receive. And so it's 6:02. At this point, I believe we have to start, we have to proceed. So I would like to say a few words about our speaker. Our speaker for today, Dr. Dimitris Krinis, is a senior petroleum engineering consultant with over 30 years of worldwide experience in the oil and gas industry. His expertise spans across field development planning, production forecasting, water flood surveillance, reservoir fluid characterization, special core analysis, pressure trench and well testing, reservoir simulation, and horizontal well completion and performance. He holds a BSc and MSc in mining and metallurgical engineering from the National Technical University of Athens in Greece, and a PhD in petroleum engineering from Heriot-Watt University in Edinburgh, Scotland. So without further ado, Dr. Krinis, I believe we can start, and the screen and mic are all yours.
Thank you, Maria. Thank you for the invitation from the Technical University of Crete on the SP chapter, students chapter. Good evening to every one of you. I'm really glad to receive your invitation and share with you some of my knowledge regarding tonight's topic. It's a very wide subject, so an hour is not make a favor to it, but I'll try just to give you a flavor and introduction to it, get a feel of what a petroleum engineer is going to be doing if he joined an operating company. And hopefully will generate some questions which I can elaborate later on at the end of the session. But before I start with the technical part of the presentation, of the talk, I would like to share with you a little bit about the global outlook of our industry, of the future of oil and gas industry. There is a lot of things going on right now about the industry and its future. Why is it not moving? Okay. This is a chart that gives you a feel of the demand of oil demand over the next 30 years. And as you can see, we are now at the dust line. And unfortunately, due to pandemic, there is a low demand, but hopefully this pandemic will be behind us in the coming year. And you can see after that that we can have a 15-year period of constant demand. If we look on a separate in a different way, this, which is now is not the production but the energy demand in quadrillion British thermal units, you can see that the oil will stay constant and then will decline after 2040, where the gas demand will continue rising. In summary, if we just look at 2040, the prediction is that hydrocarbons still will be will cover half of the energy demand of the globe. So given this, you can make your own mind about how bright the future of the oil and gas industry is. So let's share with you now the part of the technical presentation. And here is an overall chart that gives you an idea of, in terms of a timeline in the x-axis, the type of production and activities we have, and the bottom one, the money that the company has to spend to make this product, to realize this production. I will only cover this part. I will not talk about exploration, discoveries or appraisal, but we'll start from the moment that the decision has been made to develop this field. And you can see before even production start, you have to sink a lot of money. This is called CapEx, capital expenditure. And as you go along, you have to pay your taxes, royalties, and OPEX, which is operating expenditure. And this blue color gives you a little bit of a feel of the profits that the operating companies will make. So this is just the main items which I highlighted just for you to be familiar with the terminology. CapEx means the facilities, the drilling cost, and so on, where OPEX is the energy we consume as we move along, the cost of the transportation, and so on. Royalties and taxes go to the state, who is the owner of the resources, and of course the profits of the company. Here I give you a feel of what is, in general terms, the type of hydrocarbon accumulation where we have and where they're located. And as you can see, you could have onshore, offshore, and for your benefit, I added Arctic because maybe in the future that would be a hot area that the oil companies, they will move into it. And then we have the type of hydrocarbons, to where there is oil, gas, then there is within each type of fluid, we have saturated, undersaturated. I'm assuming that you have some understanding of these terms. I will not elaborate more, otherwise we'll be here for 4 or 5 days instead of 1 hour. If it's a thin oil rim, if it's light hydrocarbon, intermediate, heavy, in terms of gas, dry, wet, condensate, critical, in terms of size, small, big, and giant fields. In terms of rock type, we could have sandstones, which are sometimes referred to as clastics. We have carbonate reservoirs, and we have natural fracture reservoir. Mostly are carbonates, but let's put it as a separate category. And then we have the characteristic of the structure. What type of structure it is? Is it layer? Is it fracture? What is shapes? Is sort of a nice rounded one, or is an elongated? What the dip is, the angle of the formation. So the main thing I like you to take from this slide is that there is such a variation. So there is no unique, or every field is unique, and every field needs its own attention and way of approaching its development. By no means these characteristics I put on this slide cover the whole subject, but it gives you a flavor of it. Let's, for example, take, let me move this because, why the location and the shape of the accumulation or of the reservoir matters. Let's assume that we have discovered a field and we have appraised it, and it has an elongated feature, an elongated shape. And let's assume that as one scenario that is an offshore field. So as you can see in the picture, we can go to any location, assuming that is in a not inhabitable area, as I don't know, a desert or a steppe or something that there is no population on top of it. So we can go to any location and we can drill and we extract the hydrocarbon. So the decision you have to make about how to develop these fields, it could be phased. We can do part of it, learn, test, and move on to the next one. When it comes to facility where they're gonna process the hydrocarbon, they come to surface. Again, we can build one that will, let's say, will cover our original, our initial capex and opex, and then if the hydrocarbon accumulation proves to be bigger, we can expand. So there is room for decisions to be made in a phased fashion. And then we would not have any problem with the location. You can always, of course, move a little bit, one well there and one well here, but we don't expect major problem. The evacuation routes, of course, can be because this area it might be isolated. Maybe there is no facilities. Let's say if it was in Texas, then I'm sure there would be a pipeline passing by, so there wouldn't be an issue. But if it's somewhere in Siberia, maybe you need to spend money on pipelines. Then with regards to the maximum liquids you have to process, since you will do it in a phase way, you can always increase and maximize the liquid capacity you have to do without spending a lot more money. Then you can also decide later on to whether you're gonna do water or gas injection. So overall, the capex is high, but compare it to the offshore scenario, it's lower, right? The environmental issues, I think they apply to both cases, although offshore might be somewhat higher. So let's go to this is the sort of a picture of the elongated feature. It's a real reservoir from the North Sea. So you can see that one platform, it will not be able to reach the whole accumulation. So you may have to go for two platforms. These days, the technology of drilling wells and reaching far away from the platform has increased. So instead of the solid circle, we could reach the dash circle, for example. But still, we cannot reach to the most southern part of the field. So we have to do another type of facility to take that oil. So these decisions have to be made ahead of time, and they cost a lot of money because you have to put the infrastructure, the platforms in place. And that's a capex that it has to be taken into account. When it comes to the number of wells we drill, this is the picture here I show you. I hope you can see. These are called conductors, and they are limited numbers on each platform. You cannot drill more than the conductor. So you are limited. So you have to make sure that every well, it meets its objectives. Where in the onshore case, you can always drill another well if some well it did not perform as expected. The distance to evacuation pipeline is also important. If you are in a mature basin, like the North Sea, there is always a pipeline nearby. But in other areas, let's say East Africa, which is a new hydrocarbon area, there are no pipelines. So they have to spend money to lay the pipeline. Now, when it comes to, again, the maximum liquid rate, you have already made the decision because you have built the facility. So there is no much room to handle more fluids. So it's a very critical point to get this right up front. So you size your platform and your facilities correct. And then also you have to make a room for gas or water injection ahead of time. As you can see, and you expect that you have way much more capex than in the case of the offshore, the onshore case. The environmental consideration is a bit subjective. I think it's more for the offshore, but it depends on the area, the onshore facility. You can have, though, cases of reservoirs and fields that they are somewhere in between, not offshore, not onshore. And like in this picture here, if the water level is very low, let's say 10 feet, like 3-4 meters, you cannot put a jack up there to drill. There is issues with that. So you have to build this infrastructure, which is artificial islands to put your well. Or like in this scenario, which is from the UK, you see that this is I'm not sure if you can see it very well, but this is water, where the rest, the darker color, is land. So they found some area here where they could drill the wells, and you can see these red lines represent horizontal or extended reach wells, so they can reach the far end of the field. Because again, due to environmental issues, they are not allowed to drill offshore. So you can have this scenario, which is add to the expenditure of the development. So again, I give you a very big overview of what's going on. Definitely, there are much more issues one has to consider before you proceed with the development, but that's, you get a feel of the difference between onshore and offshore cases. Now let me go into the development. Typically, people that are not familiar with the industry, they will ask these questions of how big is the accumulation, or how much can we get out of it, how quickly you can get out of it, or how much money you're gonna make out of this accumulation if we develop it. In our technical terminology, it's a little bit different, right? We have to say we have to assess the hydrocarbon in place. And this abbreviation here, I'm not sure if you are familiar with it, but this is hydrocarbon in place, stock tank oil in place, and you can see down here, I have put as a reminder, what do they mean? We have to estimate the reserves and the recovery factor. We have to generate production and injection profiles for oil, water, and gas. And it has to be done in a way that is profitable. Otherwise, there is no point developing hydrocarbon. So we have to assess the economics, the cash flows, the net present value, and make sure that we have all this done properly calculated. There is one thing here, which is the oil price forecast. And unfortunately, nobody can predict accurately. And there have been cases in the North Sea where there has been a very technically successful project, but it might not have made money for the company. So, and that's because of the oil prices. And unfortunately, the oil prices are a kind of volatile. And you can see a few months ago, I'm not sure if you follow very closely the industry, you have to pay to get rid of your oil. So it was negative price. For the first time in the history, the oil price was negative. So you are selling your oil and you have to pay somebody to take it off your hands. Okay, let me go through just some example of each part of the assessment we have to do. Let's look at how do we assess the hydrocarbon in place. There are two types of data we have to use. Some of them, they are called static data, and to just get you into the terminology, static data means data they don't change, like the structure is unlikely to change, right? The gross rock volume, which I represent here with this bar, is unlikely to change during the field life. Then the porosity, 99%, it would not change. So there are a few things that they don't change during the development of the field. So these are what we call static data. And here I give you an example that the gross volume might be this big, but when you remove parts of the reservoir that we call non-pay, then you have the net pore volume, which is smaller, and then you have the hydrocarbon per volume, which is even smaller, and then you have the oil in place, which is what it really counts after you perform the hydrocarbon evaluation. Now you can have additional volumes that you were not aware when you started, because as you can see in this map here, there were different fault blocks that you could not evaluate during the appraisal phase of the reservoir, but later on you could drill wells, step out wells, like for example this well here, this black dot, or you are lucky and you find reservoirs in deeper horizons than when your target one is. Addition to hydrocarbon volumes can come from new surveys, new seismic surveys, especially 3D. So your oil in place might not always stay the same. Not necessarily goes up, it can go down. So it's a balance between what you find and what you know, what you have guessed, and so on. Then all the time, as part of our job, not the petroleum engineer alone, but the geologists, the petrophysicists, all the people involved, is to evaluate the data and add into it the dynamic data. What do I mean dynamic data? Data that change with time, like production data, pressure. We drill additional wells, so we get more information. So these are the so-called dynamic data. Now let's look at the fluid distribution. We are all aware if we have water and oil, and it's only gravitational forces play, there is a very nice separation between oil and water. However, the oil is not in a void in the reservoir, it's more into small pores inside the reservoir. And as you know from your basic physics at the high school, the thinner the capillary is, the higher the oil-water contact will rise, right? And this picture here shows you in a graphical format how do you expect to be in a reservoir. So we have both fight, if you wish, between gravitational forces or buoyancy forces with capillary forces to equalize the fluids, meaning oil and water or gas and water. So we have to evaluate this, and there are a lot of engineers and geologists and petrophysicists involved into this part. Also, it's very critical to find out the free water level, the oil-water contact, the gas-oil contact, or the gas-water contact. Depends on the type of the reservoir, because this will quantify the overall hydrocarbon volume, which I talked earlier on. How do we get this? We have something we run in the wells. We call them logs. There are different types of logs. Here I give you a trace of a resistivity log. And here you will see 3 different logs they put together: gamma ray, neutral and density, where you get a feel of your porosity. Again, we just quickly brush through this. If you have any question, well, I could add a little bit more. But there is also another tool which is very useful. This tool is relatively new in the oil industry. It's, I would say, since the mid-70s. So if you work in a field that is predate this, you cannot have this type of data. And you will be surprised if you work in the industry worldwide. There are still fields that they are still on production since the 50s and the 60s and so on. Anyway, going back into this, what that tool, which you see an image of it, you take pressure at different parts of the reservoir and you see the gradient, and from the gradient you can figure out whether you have water, oil, or gas, and where the intercept is either the gas-oil contact or the free water level. Not necessarily the oil-water contact. Can be the same, but not necessarily the same. Here I give you an example of something that 2 cases, 2 scenarios. In one, as expected, the oil-water contact is a flat line, which means there is an equilibrium. The fluids are in equilibrium in the reservoir. But In reality, you will find a lot of reservoirs around the world that this contact is not flat. And this is due to this hydrodynamic environment or effect. How can we tell the difference between this tool here? The formation tester can give you a hint of it. If we take pressure in this scenario, you would see the oil gradient and the water gradient. Where in this scenario, if you have these three wells, you would see three different water gradients. That would be one hint that most likely the contact is not flat or the free water level is not flat. I have to say, when I was a student, I never heard of this thing, but as I work in the industry, I realize more and more reservoirs, they don't have a flat oil-water contact or free water level, which is add to the uncertainty of calculating the oil in place. Other information that they can add to determination of the fluids is cuttings. We can see if they have oil stains on it, and seismic data can also provide some hint of the contacts, although they are not reliable. They have to be verified by the logs or by other means. Let me now move into both hydrocarbon fluids and other fluids in the reservoir. I'm sure you are familiar with the API gravity, which is a property of the oil when it's at surface. And then its composition. Here you see a chromatograph where you can see how many types of hydrocarbon we have, if we have any contaminants like CO2, nitrogen, or H2S, which we don't like to have, but sometimes you do. Obviously, we need to know its density, both at surface and at reservoir, the gas-oil ratio, if we are talking about the oil field, viscosity, compressibility. Here I give you an example of the different type of fluids, from dry gas to volatile oil to black oil, and this is the phase envelope. Typically, the reservoir you're gonna encounter, if you work in the industry, is around this yellow belt, although it can be other parts of it. But what is important is to know what is the initial pressure of the reservoir and how that relates to its to saturation pressure, or in this case, it's oil to the bubble point, and how we're gonna reach from here to the test separator, because different paths that the hydrocarbon follows, they can give you slightly different properties. And we always try to make the BO, which I don't have here, the formation volume factor, I forgot to add it in that list, that will give you more oil in terms of stacked oil barrels. So they will give a little bit more higher profitability. One other thing that it doesn't affect so much the petroleum engineers, but affects a lot the people that they design the facilities, and they will ask you to provide this information. Although they are not, you don't need them yourself for subsurface calculations, but for surface, they will ask you if there are any heavy metals or so on. So you have to be aware of these things. Now let's move to the formation water. This is a very important aspect. People tend to focus more on the oil and gas property and ignore the water properties, but it's very important, and later on I'll show you why this is important. You need to know its density, viscosity, its compressibility, and its geochemistry, right? How many dissolved salts you have in there, or these particular elements here, which are very small, but they play a key role, like barium, strontium, and so on, sulfate. Later on in the slides, I'll come back to the subject. Right, now we get a feel of the basics of the reservoir. Let's talk about another thing which is important. What kind of energy sources there are in the reservoir? Because the oil is down here, as you can see in this picture with the green color, but the oil has to travel from this depth to the surface facilities. And this could be up to 6,000 feet or 2 kilometers, or it can be double that. So he has to have some energy inside the reservoir to take this hydrocarbon to surface. And of course, there is energy. So this is what we call lifting the hydrocarbon to surface. And this energy also helps you to move the hydrocarbon from the reservoir, from the port to the surface. So let's look at it, what type of energy sources there is. Since the oil always has some gas dissolved into it, like the, I don't know, the Sprite or the Coca-Cola fluid inside the bottle, it contains gas. So if you shake it, you will see that it will, when you open it, it will flow out of the bottle. The same with this, there is some gas, so it provides some expansion into the oil and might be able to bring it to surface. And as the pressure drops, that gas, it will come out of solution and provide, again, a little bit of energy to bring the oil to surface. A major source, though, of energy is the aquifer, or the water that is in the fringes of the oil accumulation. Not always strong, sometimes strong enough to get all this energy that you need to bring the oil, but sometimes not, so we have to support it. You know, there is some compressibility in the oil and the water that can help you a little bit, not that much. Then the rock compaction, as you release pressure, the rock may compact. In most of the fields I have worked, there is no such an issue, but there are some cases in the North Sea in the early days of production in the North Sea that the compaction was strong enough that the platform starts sinking. So they have to raise it up. Then we have gravitational forces, which can assist mostly with the sweep of efficiency of the hydrocarbon. And of course, we can have a combination of all these things. It's not just one, it can be a combination of all or some of those things to bring the oil to surface. This is a typical recovery range you will get if only one of these energies apply to your field. And you can see if we only expect to bring oil to surface by compression, you will get just 2% of the oil. The rest will stay in the reservoir. Compaction, you have a little bit more, solution gas drive a little bit more, and so on. Let me share this in a graphical format. So the green, or this bar here, I'm not sure if it's very clear into your screen. We call it primary, meaning we not apply any engineering energy into the reservoir, but what is there. And you see it's reaching about 20%. But most of the time we do what is called secondary or water flood. So we inject water, we complement the reservoir energy with injection water. So we try to extend this plateau from very little to a long 5-10 years, and we can have this kind of production profile. So we said it, we improve the energy so we can lift the capacity and we can sustain the production. There are some other benefits which I put it here, but I will not elaborate more. And we increase also the recovery. So we move from 20% recovery factor, maybe to 60%. So we double basically the amount of oil we're gonna bring to surface. And that will have an effect on our net present value and the revenue that the company is gonna make over the field life. Now, the question is, can we flood every reservoir? This is funny enough. This is a question I ask at the interviews when people apply for a job. I ask this question, and you will find that not everybody is capable to give you an answer. So this is two examples of the reservoirs. This is a cross section, and this is a 3D image of the reservoir, and I'm not sure if it's very clear again into your screens, but I will tell you what we see there. So depending on these things, we can say, if this aquifer is weak, then we can supplement it. So we need water injection. Then we cannot do successful water injection if we have very high viscosity oil, let's say 20 centipoise or more. There is something which is a little bit more technical, and I'm not sure if you know the terminology, is mobile ratio, which is this equation here gives you the mobility ratio. We want this to be less than 1 or close to 1. This is a very good reservoir to do water flooding. The other thing we look at is the heterogeneities of the reservoir and the stratification. I'll come back to this, what exactly mean, but you understand what heterogeneity is. And the other last one point I have here is we don't want to be compartmentalized like this. You see this reservoir down here in the picture I put it is completely broken by faults. So there is unlikely that these different fault blocks, they will talk to each other. So if you drill an injector in one block, you will not be able to support the other block. And this is happening in many parts of the world. So this is just again a flavor of what we need. So to come up with a development plan, you have to answer these basic questions. What is the production, the plateau rate, right? Because that's the part that will give you most of the income. How many wells you will need? Where are we gonna put the wells? And what size of tubing we're gonna put? What kind of completion we're gonna put? Do we need artificial lift and so on? So I will try to capture some of this as we go along. And one of them is the plateau rate. So we try to expand this as long as we can, from 5 years to 10 years. And how do we decide this? Of course, there is a lot of parameters come into it, which I have already mentioned, right? Onshore, offshore, size, and so on, heterogeneity. So you need to do a full evaluation, and all the subsurface people or professionals have to be involved. Reservoir engineers, geologists, simulation engineers, this uncertainty analysis. You can, as an experienced engineer, to use some kind of first estimate by using statistics from other fields in the world. So this chart gives you the ultimate recovery in million barrels. So if you have a field of 100 million barrels, you could see you could extract from it 8% of its original reserves per year and use that as a plateau rate. It's not bulletproof, it's just a first estimate. So once you know what kind of plateau rate you target, and you know from something which again I would say a little bit more later on about the well productivity, you can divide this by the well productivity and you get a feel of how many wells you will need. Of course, the shape of the field is important for that. Okay, here is a few examples of it. This particular field, for example, you see they had a nice plateau rate for 10 years, and then they declined nicely. And they depleted the reservoir 10% of its remaining reserves. Where this field, they were starting at this level, and then they thought that's not enough. They are depleting in at 2%, and they moved to 10%. Look at what happened to it. It could not sustain this plateau rate. And this is the ugly field where there was no plateau. Obviously, they have something went wrong in the development of this field. They had miscalculated. I don't know exactly what. I'm guessing that the oil in place maybe was not properly calculated. Or they were too greedy and they tried to pull 30% of its reserves at the plateau rate. So you get the feel of how methodically you have to be to decide on the plateau rate. Let's give you a feel about the wells and the type of wells we typically we want to drill, and that depends on the type of drive we have. This is a bottom drive, meaning the water is coming throughout the whole area of the reservoir. Or we can have in this cross section here, which is across this reservoir, we have peripheral injection, meaning these are the injectors. The blue are the injector and the producers in the middle. or you can have line drive. A lot of, you see the wells are aligned to each other. Or you can have pattern drive, not very common in offshore environment. Or you can have reservoir dictated, because the reservoir is so much faulted that the fault dictate the well location. Let's give an example of, this is the three cross section of reservoirs that you see. Here we have oil and water, here we have a little bit of gas, and here we have a lot of gas. The way we put the well location is different from one to the other. In the first one, we try to keep it at the top to be away from the water, so we don't produce a lot of water, but at the later stage of the field. In this case, somewhere in between, depends how big the gas is and how strong the aquifer is. And in this case, where we have a lot of gas cap, then we try to put it close to the water. And in this case, horizontal well technology have come into play. So that's how you would develop a field like this. If it's an edge drive, meaning the water coming along the deep of the reservoir, you could have, in this case, moderate deep, here kind of flat reservoir, and here a reservoir with average deep, but it has a transition zone. So you can see that how you configure these wells. I will not elaborate why we do this, but I give you a feel of these parameters are important to consider. This is another issue you have to handle if you have a layer reservoir, and depends layer 1, layer A, B, C. Normally they name them. Depends of the vertical permeability. KV stands for vertical permeability. If it's good, you can put a horizontal well somewhere here, but if it's not that good, then you could put a slanted well that penetrates all the layers. And if it's low, you might need to go for vertical wells and more wells to do that. If the layers are not talking to each other, they're isolated, then you have to have a drainage point on every reservoir, because effectively you have different reservoirs. That's why we call them stacked reservoir. And this is a kind of a detail how these completion look like. They're a bit complicated. So you have two tubings in this well instead of one that you have in normal scenario. And you have something that I call sliding sleeves. So you can produce one, and then you close this one, you open this one without having to do any workovers, which are costly. Let me give you now another feel of how this development is not something that is it's decided in the beginning and it never changes. And that, why is that the case? Here's an example of a reservoir structure, right? You can see the contours here. They give you a feel of the structure. So when they mapped this, they had a 2D survey and few appraisal wells, right? Back in '88. And then few years later, they drilled some more wells, and as you can see, the structure now is a bit more complicated, and it doesn't stop there. They drill more wells 2 years later, the structure again changed, and few years later, they did another, more wells and another 3D survey, and look how this one ended up. Compare the two. If you had planned your wells like this, and you said, okay, I do peripheral water drive, okay, it looks great, but 5-10 years down the road, if you maintain that plan, it will not be very successful. So it's a constant review and update of the knowledge that you acquired during the field development to have a successful development. There is a lot of things you can do to acquire this knowledge. Pressure transient analysis is one of them. Is how the way that pressure propagates in the reservoir while you produce it and then you shut it in. So you produce here, the pressure drops, and then you shut it in and you build up the pressure. You can analyze this. We use some specialized plots, pressure and derivative, and from the shapes of these curves, you can tell a lot about your reservoir. It can tell about the well productivity, how damaged it is, your permeability thickness, your reservoir pressure, and a lot of other characteristics, how big the reservoir is, if there are any boundaries, any heterogeneity. This is a whole subject of petroleum engineering, but very important to decide. For example, in this scenario, they drilled these two wells and they found this sand, and they wanted to know if this is communicating. So they did this pressure buildup and they found out that this profile on the derivative tells them that they're in communication, because if they were, this curve here would have continued to go up. Let's move to another subject, which is a daily routine thing that it happens during your everyday work. You evaluate the performance of your wells and the field, and how you forecast what is going to be the production in 5 years time, 10 years time, or to the end of field life. We use a different specialized plots for this. I will not elaborate. We use material balance, we use decline curve analysis. So the red line, for example, tells you how the well declines, or it could be the field. And then we can extrapolate the last trend of the production data. And we have different ways of extrapolating, either exponential, harmonic, and in this case, the ultimate recovery, that's UR stands for, it could be here, it could be there. So you see quite a big difference. In terms of water, you can plot this kind of, can make this type of plot, time versus water oil ratio, and you can extrapolate and get, again, production profile and cumulative production. Of course, these days, there is a simulation model for every reservoir, so we use that. And like we discussed earlier on with Mario, machine learning or AI has come into it. You can teach a model maybe to help you identify the type of wells and how it will behave in the future. The other thing that preoccupies the engineers is the how much oil we're gonna recover and how much oil we're gonna leave in the reservoir. Earlier on, I gave you this chart that it says if you do primary, you will recover 20%. So 80% of the oil is still down there. So you want to make it sure, or can do whatever is possible to leave less oil in the ground. So things you will do is you could drill wells in parts of your reservoir that has been already flooded to see, to measure how much of remaining or residual oil is there. You can take sidewall samples. You can do special core analysis. And then there are a lot of logging things. You can have the resistivity, dielectric. Unfortunately, I have no time to explain which one of these is what it does and the constraints and so on. Then you have the formation tester, which is already talked. You have pulse neutron that could help you, and production logging, which is give you the profile along the well, how much water is coming from which part of the reservoir. One thing I want to highlight is these logs are done when you drill the well, so they're called open hole log. And these logs are important if you have mixed salinity environment. Material balance is another technique to figure out in the residual, the remaining oil, and reservoir simulation always is an important tool in the hands of the engineer. More sophisticated, but surveys that we can do, but it's not done very frequently. The logging is done frequently, but single well chemical tracing, 4D seismic, or interwell electromagnetics, they are not done very regular because they are very cumbersome to execute and costly. Let me give you a little bit of feel of the development, the advancements that have been over the last, since I started my career about 30 years ago. Those days, the only well they used to drill was vertical wells, but now we can drill horizontal wells. And here you can see different types of horizontal wells, from single lateral to multilateral, meaning it has more than one lateral. So the the horizontal drilling has, and the tools that they achieve this, they have increased tremendously. Here is extending Reed's well. This well here, it can go up to these days 40,000 feet. That was not possible 20 years ago. Then to reduce costs, we have a coil tubing drilling. It's a very complex process. I will not elaborate, but I would like to give you a feel of, again, how much the advancement. In the old days, you would not be able to drill that well. It would be just a straight line. But now, with something that is called geosteering and formation evaluation, while you are drilling, you can steer the well to go and follow the best productive layer, like you see in this example here. Further to that, the technology has also improved in terms of drilling, but also getting pressure and temperature data using putting in place sensors that they will give you this data. In terms of the well completion, because we're drilling a lot of horizontal wells, and horizontal wells could suffer from coning effect. This blue here is that the water could come at the heel of the well. So we can put different types of hardware there. They call either inflow control valve or inflow control devices to mitigate any coning effects. This is how it looks like, these kind of devices. Let me quickly move into reservoir management, because this is the part that you're gonna be doing on a daily basis if you join the industry. You might not be able to, or you might not be lucky enough to join a reservoir in the very beginning of it to see all these things I discussed earlier on. So, but you will always be able to work on these things, which is when you have production, you always want to produce oil, but unfortunately, we produce a lot of water. And just for your curiosity, I normally ask this question, but now we don't have we are not face to face, so I cannot ask this question. But typically, for every barrel of oil we produce worldwide, we produce 3 to 5 barrels of water. So water is the constant battle. Try to eliminate the production of water. So you have to be able to evaluate your well performance and see if the water influx is gradual or is sudden. So in this case, I'll give you some examples of gradual water influx. It could be due to coning or to cusping. It could be due to water rising, especially if we have oil water rising, we have bottom drive. It could be because one layer is very thin and very permeable. We call them thief zones. So water from the injector will go straight to the producer. Or this, again, looks very similar to the previous one, but the thicker parts are not so permeable, or they stop to be permeable, so the water will find its way through here, or through fracture, or through fissures, and so on. And this could cause not very nice aerial sweep. So the red represent where the oil has been left, and you see 10 years later, 11 years later, there's still oil because we didn't have very good aerial sweep for this reservoir. Or due to gravity segregate layers, then the water cannot go down and effectively sweep this oil. Here I give a feel of what kind of possible remedial actions we do. To avoid coning, we can reduce water draw rate, which will reduce the drawdown. We can put plugs, water shut off with mechanical or cement plugs. Here I give you a feel of what the plugs look like. If we have thief zones, maybe we avoid to perforate those, or we shut off the injection into this zone, the direct injection into this zone. If you have these things, you have to manage sometimes. You cannot always isolate. And even if people tell you that, yes, service companies have the the ability to come and try to sell you products, and they say, oh, you know, we can do some gel injection, and we block these unwanted zones to produce water. It's not always successful. You could have adverse effects. In terms of aerial sweep, you can divert the water injection, you can change your injection, you can maybe drill another injector, or you can sidetrack existing wells that have been watered out to areas that you think is lagging oil. The same thing I kind of applied to this. Now, what about if you have sudden water influx? I have to say, when I went for an interview 30 years ago, they asked me about this sudden water influx. They told me, what do you think is the problem if the water cut goes from 0 to 50%? And unfortunately, I could only think in terms of gradual water influx. I did not think of sudden water influx, which it could be caused due to channeling effects behind the pipe. They did not do a good cement job, so the water goes here and then finds the perforation and goes in. Or more common, you have kind of corrosion or some leakage somewhere into your tubing or your packers and so on. So this is how you tell if it's sudden, because you see a big jump in the water cut. It could be related to fracture. If you fracture your well, you want to contain it within the oil zone, but unfortunately, sometimes the fractures could go into water zone, and then you will get unwanted fluids. Formation, deformation that could cause parting of casing or of tubing, and reservoir depletion or excessive pressures into the tubing and the wall integrity and so on. So again, in this case, you can do some remedial action. You can squeeze cement or gel. You can squeeze, again, the same thing, or you can do a workover. In the corrosion, you can do inhibitors, meaning some substance that would stop the fluids from corroding the pipe. Again, all this is more of a management. Try to avoid it. Try to have a better QC on whatever you do, the completions, or when you do the fraction, you have better control. There is not always, you cannot solve these problems 100%. You can mitigate them. This I'll give you an example of how the water cut looks like, and from the shape of these curves, you could figure out what type of problem you most likely has been encountered by the well. So the letters next to the type of problem represent the curve. So if you have a curve A, it could be like that. If you look at the curve C, okay, yeah, I don't see a C here. I think it's more of a gradual thing, but this is a constant day-to-day work. You make plots. This is a different type of plots you can make. Logarithmic plot of water oil ratio and the derivative. That dot stands for the derivative. And depending on the shape, you can say if it's a channeling, if it's a water oil duct rising or bottom water coning. They are not as straightforward as they look on this chart, but through experience and through comparing wells to each other, you can figure out if any of these problems, the well suffer any of these problems and mitigate it. Now we come to the formation damage. In the very few beginning slides, I mentioned something of the water composition. Depending on how many salts the formation water has, it can precipitate scale, which you can block, as you can see in this picture, your tubing. And some of these scales you can dissolve it with acid, some others you cannot, like barium and strontium, you cannot. So you have to pull this string out and replace it. And of course, that's 5 million job. It's not just something simple. So you try to avoid it. You could have the same problem with asphaltenes. Here is a picture of it. You can have emulsion and plug-in. You can have all type of solids moving, sand moving, clay swelling, fines migration, all sort of things. Changes in the saturation due to adaptability reversal and so on. What can you do? First of all, you have to understand these things ahead of the game, before you have the problem. And if you have the problem, you could do some inhibitor squeeze, you can do some stimulation, try to avoid, to prevent, rather to remediate. You can, here this picture here, so you can reperforate, there is some jetting you can do, and so on. I think it gives you a feel of a lot of activities going on each well, and each well it has its own characteristic. Let me give you, I think this is my last slide. The subject which is very important is reservoir surveillance. To avoid and mitigate something, you have to monitor data. Otherwise, if you don't have data, you cannot provide an answer to the questions. So the routine data or the routine surveillance that happen in every well is to get production data, oil, water, gas rate, right? We have, here is a separator, so you can measure your oil, your water, and your gas. Typically it's done once a month. You can take pressure gradient data. Maybe this is done maybe once a year, maybe a little bit more frequent, but this is important. Just knowing different pressure data over time. Let's say if we monitor this data and we see the black points, right? We can tell that in the beginning we have depletion drive, and then we had solution liberation, solution gas liberation, and then we had injection where the pressure started going up. Now you might say, what happened with this orange point? Oh, this well, it doesn't belong to the same reservoir or to the same block like this one. So you have to treat it separately. This is another type of logs we do kind of regularly. I would say once a year, maybe once every 5 years. Depends how quickly the water comes into your well. But it's nice to have one in the beginning so you know exactly when the well was dry, meaning it didn't produce any oil, and how it comes later on. You do the same things with the injection. You measure the water you put in the reservoir. And the cheapest of all the measurement you can do is you analyze the water that you produce. Based on the geochemical analysis, you can tell a lot how the injection water or the aquifer moves inside the reservoir. It's the cheapest way of doing it. And I have some jokes to share with you, but maybe we have time, we'll do that later on. I'm already over the hour. So we can have a mechanical problem, which I elaborated on. But these days, the technology has moved. And you will not be, I will not be surprised if you work in a field where you have production data not once a month, like I said here, but every second, every minute, because we can have a measurement, a continuous measurement of the fluids flowing. Here is, for example, one of these surface measurement of rates, or we can only measure the water cut, or we can have gauges downhole to measure the pressure all the time, every second. We can have the fiber optic distributed sensor, where we can know in a horizontal well, for example, or a vertical well, which every zone what it produces. The problem with this thing is you are overwhelmed with data. So you have to have some kind of a system to filter out the volume of the data that you have to something that is manageable. Otherwise, it's a new task, and I think here there is room for artificial intelligence to help. Oh, I do have one more slide. It seems the surveillance is costly. It's part of the operating cost, so you have to target it, especially if you want to do something like pressure transient analysis, because in this scenario, you're gonna shut in the well, and your management would not like to shut in the well because they're losing revenue. or they want to run saturation logs, or you need some more sampling because your PVT properties, fluid properties that you have, they don't look very good. They don't match the GOR very well. You need to know what is your endpoints in your relative permeability curves, and so on. Again, as you drill new wells, we call them typically infill wells, you have to run open hole logs and saturation logs. With that, I conclude my presentation. I hope I did not overload with information. This is basically what you will be taught in a year. I try to squeeze it in 1 hour. I hope I gave you a flavor of it, and I'm quite happy to answer your questions.
Thank you, Dr. Krinis. I think the presentation was really good and understandable. The first half was a gentle introduction, so I believe most of the participants, which are undergraduate students, could understand it fully. I want to start from the end, where you mentioned the DAS, the distributed acoustic sensing technology, basically with fiber optics. And yeah, so you use that in Saudi Arabia, because my thesis was in that for my undergraduate studies. And back then, most companies, because of cost, because of data, they didn't use it so much.
Correct. The problem with all this technology is that it needs new tool to analyze it. And it seems that the hardware are ahead of the software to do the analysis. So you get information overload, and the system is not capable to get useful information like this. So you have to depend on the service company to provide the analysis. And this creates somehow a difficult between the operator and the service company into justifying the cost. So we have run some of them. I don't know if we truly get the value of information. Unfortunately, I'm not involved directly on this project, so I cannot give you any, more feedback that this general view I have about it.
Okay, thank you. Adonis before mentioned that in his company in Aberdeen, for scale, they use electromagnetic interference to clean the scale. As far as I know, most times it's used some chemicals. There was some solutions I remember from Weatherford also for electromagnetic interference, but I don't know. Do you use that down there?
We don't have that kind of issues. We don't have scaling or other issues, so we haven't used that. To my knowledge, we haven't used it, and I never use it throughout my career. I'm assuming it's something relatively new.
Okay.
The thing we use, which is standard for the industry for not centuries, for the decade, is acid.
Standard chemicals, that you soak it.
Yeah, you inject an acid pill, that's the terminology, and you soak it for, I don't know, 24 hours, and you hopefully remove the scale. But if it's hard scaled, the acid don't do a good job. Maybe you can go with something to drill it out, or very expensive operations.
With coil tubing to drill it out, or?
You can use coil tubing, yes.
Because you mentioned also that you use coil tubing to drill.
Yeah, this is the new trend. People, every time you want to do a workover, if it's on land, it will cost you, let's say, $5 million. If it's offshore, they cost you 5 times more. And if it's a subsea completion, which I haven't mentioned at all, but that could cost you millions of dollars, 20, 30 million. So you try to do everything to avoid of happening.
Okay, I have a question here saying what What's the strategy do we follow to produce a formation without a clear GOC where oil and gas coexist in a hypercritical state throughout the column?
Okay, you have to figure out when the fluids coexist and you think that you're going to produce a lot of water. Sometimes it's misleading. The saturation, the fact that it's high saturation, it doesn't mean that you will produce a lot of water, because this water might be attracted to the formation and it doesn't move. So I'm assuming the question rises from areas where you have either a big transition zone or very layered, very thin layers of reservoir and non-reservoir, which at the log, this is get average and gives you higher water saturation than the actual is. The so-called high resistivity, low resistivity pay. So, okay, I didn't answer. So the question is, you have to run specialized logs, have a proper look at the analysis of this log and decide to whether this water is movable or not. These type of logs are NMR logs that they can help you with this type of analysis. I'm not sure if I covered the question. This type of log, NMR.
Okay, let's pass to another one. It's about if you could elaborate a bit more in pressure transient analysis and how to interpret tests from several layers with commingled flow.
It's not always easy to do commingled flow. Yeah, you have to know. You have to do multi-rate transient analysis, meaning producing at different rates and get the response, and then try to figure out how much each element, each layer contributes. It will be a very challenging project to analyze this. I think by well test analysis alone, you cannot do it. You have to combine it, the traditional well test analysis with simulation. And these days, the package, the software available in the market, you can do both at the same software. You don't have to have a well test package, well test analysis package, and simulation separate. They can do it together. And you have to combine. Otherwise, you will not just be able, with the simple pressure and derivative, figure out what's going on.
Okay, thank you. Which packages are you talking about actually? Which are you using?
Kappa is one of them.
Okay.
They, to my knowledge, they are dominate the market.
Yes. Yeah, we have also the license in the university here for Kappa, I think.
Yeah.
Now I have some questions from the soft side, I would say. It's like, how is to live in Saudi Arabia for all those years? Are you happy with that, or you regret? Are you missing Greece?
No regrets. Otherwise, I wouldn't stay here for that long. Okay, you know, when you're young, you want to move around a lot, and every time you move, you hope to improve your financial situation, right? But as the year go by and you are not alone and you start having a family, suddenly moving around is not so straightforward. Like if you had kids at school, you know, you cannot just keep taking your kids from one school to another. So you end up later on in your career to stay put in one place.
So an advice would be for the young engineers to move now that they can. Maybe.
The advice for young engineers is to find a job that they like, get as much experience they can, and invest on their knowledge and their skills and move on. Because I mean, after all, right, the bottom line of this on the job is to improve your financial situation. And staying in a company, you cannot do that because every company has a structure. Once they fit you into the salary structure, you cannot get out of it. So you can only move to another company and go into a different salary structure.
Yeah, I agree totally.
We hope it's better than the previous one, right? I don't need to say that.
Always. I have a question from Professor Nikos Pasadakis, Director of the Institute of Petroleum Research here in Crete.
Sure.
Do you use chemical analysis to determine separate layers in commingled production?
Okay, the standard in the industry is not to commingle reservoir. So if you have reservoirs that they are prolific and they can sustain by themselves, you know, the whole operation, you try not to commingle them, right? And in some countries, even the country's legislation, they forbid to commingle reservoir. That's why I show you the example of this. Where is it? You see this example here? You might have 1, 2, 3, 4, 5 reservoirs. You run this type of completion, so you don't commingle. You avoid to commingle. So you produce, let's say, this without producing this one. You shut it in with the sleeve. But as a concept, yes, you can use that. And there have been parts of the world, especially in the old reservoirs that have been developed, you know, 40, 50 years ago. They're doing it. We are not doing it here. We are not commingled reservoir.
It's only monobores, so you don't have dual bores. Or
No.
you open and you close. You don't have from 2 zones.
No, we don't. We are not in this type of scenario. And if we are, its reservoir it's a development by itself. So we have dedicated wells for its reservoir because the reservoirs are prolific. This kind of scenario is like in Malaysia, for example, they have these thin reservoirs. They are not big. So by themselves, they cannot sustain economic development. So you have to do something. You have to develop all of them. And this is the approach they follow. Because in some respect, it's dictated by legislation of the country not to commingle.
Okay, thank you for that. I believe Professor Varoutsis have a question for us. Professor?
Yes, thank you, Marius. And I would like to thank Dimitris. I would like to thank you very much for accepting our invitation and offering us such an excellent presentation as usual, I would say. I was very impressed because I was having a look from time to time during your talk in the number of participants, and I can assure you, and I think it's very remarkable, that no one has left the virtual lecture room during your talk. So this is very much to your credit. So what I would like to ask you is actually in this part of the world, activity in even in prospecting for oil and gas hasn't really started. What is your feeling about the intention of the major oil companies with respect to their potential recoveries, potential prospects? Because we have been hearing that some of them are abandoning, you know, even discover fields because they consider they are too small. They would like to concentrate on more giant fields. As you know, Total has dropped out from the concession that they got in block number 2 west of Corfu, which they had a very promising geological formation there. What do you think? What is your impression about that? Where things do you think are going? Which direction? Thank you.
Yeah. Okay. I believe the oil companies or the hydrocarbon operators, they are in a state of panic and confusion. What do I mean? Due to the political situation and the way that the media reflect our industry is such that they're against it, right? So they're all changing names, if you have noticed. Statoil is not called Statoil now, you call it Krinis. Total that you mentioned earlier on is not called Total now, it's called Total Energies. Or yeah, I think Total. So they try to put a different picture, to place themselves in a different picture, that they are not hydrocarbon companies or oil and gas companies, but they're energy companies. And in that effort, I think they're a bit lost. They don't know where to put their investment, how to place their investment strategy. A lot of them, they want to go to renewables. So given the dismal oil prices the last couple of years of the oil industry, and the limited amount of money they have, and the game they try to play, that there are green companies, green as environmentally friendly companies, they try to divert their money or their investment into other assets than hydrocarbon. So I think we are in a kind of an unfortunate times. The pandemic, it hasn't helped at all. And that's why companies withdrew from concessions that they deem they are marginal, or they are not profitable, or they're environmentally sensitive. That's my view. I don't really claim that I understand the industry myself. This is my humble opinion about it.
Okay, I don't know if Dr. Varotis or Dr. Yotis, you have any question. Maybe you, Dr. Yotis, someone has sent you something.
No, I don't have any question from someone from the audience. I also want to thank our speaker, Dr. Krinis. It was a very good presentation. I really enjoyed it. Thank you very much.
Welcome.
Okay, I want to make one more question.
Go ahead.
What do you believe is the most challenging part of your job through all these years?
Oh, good question. Challenging part. How can I put it? I think to balance between your engineering or professional integrity and the politics that's going on.
Okay.
To give you an example of what I mean, let's say that you do your analysis, right? You give the data, you analyze them, and you think, oh, I need to do a survey, an additional survey. That will cost, let's say, $1 million, right? You have to justify this expenditure. You cannot just say, oh, I want to do this. They will say, why you want to do this? And you say, I want to evaluate this and this and this. So the next question is, okay, what are the benefits? You have to say that the benefits are positive. that you will find more oil, that you would find additional reserves, where in reality, this survey can prove the opposite. That's where your professional integrity gets on the line. Would you put down that, yes, we'll improve production by 10%, or you would say, oh, it could be 10% up, or it could be 10% down?
Yeah, that's a tough call, I guess.
And the bottom line is, depending on your answer, you could be called a good engineer or not a good engineer.
Okay, I didn't expect for that answer, but yeah, it was, yeah, very different view.
I used to work for Shell, and that was the way they handle people.
Okay, okay. So I want to make a final question. I'd like to make this question to all the esteemed speakers we have. You know, as you answered to Professor Varoutsis, you mentioned about the oil companies becoming, advertising themselves as energy companies and all the transition that's been happening. Yesterday, I saw also a post from Imperial College London, where they cancel the petroleum engineering course from next year, as well the petroleum geoscience master course. So with all this, there are many people here and all over the world that are into the oil and gas industry, want to go into the industry. They are students, master students. What would you advise to those people? What to do?
Okay, there is a lot of debate going on right now. What is the future of the oil industry, and more importantly, for young people, right, like yourselves, that they want to join the industry?
Exactly.
For me, that's why I put this slide in the beginning, showing you the projections of the energy demand, because we are all talking about energy here. And you see, the oil remains constant. The energy demand from oil is constant and the gas is going up. So I think there is future to whether you have to endure these difficult times we are going through. Is something that is difficult to say how long it's going to last. I joined the industry in '86 as a student, a postgraduate student. And the oil prices have dropped to below $10 a barrel. It took 4 years to recover. With this pandemic now, we are in year 2. It's gonna take 4 years. Would be less and less job in the industry? If you can endure this and you go through this hard time, I'm kind of confident that the oil price will recover and they might be higher than the prices we saw in 2012. It's almost reached $140 a barrel. I don't think that's good to go to that high, but it has to go higher than what we are right now.
And it's been an increase in the price since last March. It's been
yeah, because one company somehow helped on that. I would not mention the name. You can guess it.
Yes, yes. Okay, so I think it was a very nice evening, and I personally enjoyed a lot your presentation, and I believe all the audience. As Professor Varoutsis said, we didn't see people leaving. They were all on the screens. So thank you so much for accepting our invitation and being virtually here with us today. Thanks a lot.
I wish I could be present.
Yeah,
I wish I could be present. I enjoy the face-to-face interaction with the audience, but we cannot do it these days.
Let's hope that we will be able to arrange this in the near future, after September maybe. I don't know.
Hopefully. Let's see.
Let's see. So thank you all for being here with us. I hope you enjoyed as much as me. And have a good night, everyone. We have sent on the chat box our social media for next upcoming lectures like this one. So you can follow us there and you can stay tuned for the upcoming events. And this recorded version of this lecture will be uploaded later on the YouTube channel. And you can find the link on the chat box as well.
All right. Thank you for the invitation. All the best to you guys. I know it's hard times for people that want to join the industry, but I hope the best.
Thank you. Thank you.
Thank you very much.
Καληνύχτα.
Καληνύχτα.
Καληνύχτα σε όλους. Καληνύχτα.